Welcome back to the Lehigh ESE Fall 2023 Zoomcast series. This is the fourth Zoomcast covering Mr. Vikram Budhraj's seminar on the transition of power grids. Mr. Budhraj has worked at Edison International in many leadership positions, including president of Edison Technologies. He has over 40 years of experience in power systems planning and operations, reliability management, electric industry restructuring, along with new ventures and technology. In 2000, Mr. Budhraj founded the Electric Power Group and is currently serving as the president and CEO. Ava, would you like to give an overview of what the Electric Power Group's role is in the U.S. power system?
Absolutely. Thanks, Mike. Budhraj noted at the beginning that Electric Power Group, or EPG, is the leader in synchrophasor technology, having established a highly experienced team back in 2000. Synchrophasor data is a hero in the energy industry because the data is very high speed, time synchronized, and collected at 30 samples per second. For comparison, traditional monitoring devices might collect data every few seconds. This reflection really delved into the key topics and essential takeaways that illuminated the many challenges and potential solutions in the transformative journey to inverter-based resources, or IBRs. Budhraj provided some insight into the U.S. electric power system, highlighting the trends that we see for different generation sources. So these trends include a decline in fossil fuel sources like coal and natural gas, and even a slight decline in nuclear power due to its inability to compete economically with fossil fuels. However, I believe that we will be seeing an increase in nuclear in the future. Hydropower is relatively stable, and renewables, specifically like solar and wind, we see are increasing in numbers. So we have entered into a new transition of the electric industry, and this contemporary landscape is really characterized by a paradigm shift from inertia-based systems to IBRs. So IBRs are any energy production or supply that primarily operates on DC and then has to invert the power output from DC to AC to supply the energy to the grid. So examples of IBRs include type 3 and type 4 wind generation, solar generation, and battery energy storage. Therefore, the outputs of IBRs change with weather conditions and are intermittent. Unlike their predecessors, IBRs lack rotating mass and spinning reserves, which introduce a host of challenges for grid operators. In the past, energy grids were powered by synchronous generators whose problems were pretty well understood and resolved for the most part, and a few inverters that were mostly DC line terminals and small supply sources. So transitioning the grid to a large-scale inverter presence creates many new and unresolved issues that require a comprehensive understanding of the dynamics that are involved. So I'll stop there before I go into anything else, as I believe Jessica will go into more detail on the challenges of IBRs. But in the meantime, I will hand it over to Alex to discuss industry experience with IBRs.
Thanks, Ava. Although IBRs haven't fully penetrated the grid yet, utilities have started to respond to the problems they've been posing. I currently work for a solar company based out of upstate New York. We work closely with the local utilities as we install 5 megawatt distributed energy generation solar fields. The other day, National Grid, one of those utilities, hosted a call focusing on the challenges IBRs will bring to the grid. Although they are still studying the issue, they estimated that 20% of the energy mix is enough to completely destabilize the grid. Why is 20% penetration enough? Well, renewables are intermittent. So if too much of your load is coming from intermittent power to the grid, then the supply is going to fluctuate greatly, especially as little things like clouds are going to come over. That can be enough to impact the supply of a solar field. Now, if 20% of your grid is like that, then grid operators are going to need much more accurate weather models to focus on models for production. And the more accurate the models are, the better the operators will be able to schedule when they need to ramp up traditional generation to help that out. Grid operators will also need more sensors, remote controls, and basically just AI to be able to control these distributed resources. Unlike traditional power plants, which range from 100 to 1,000 megawatts, solar wind farms are frequently from the 5 to 100 megawatt range. So more distributed generation means less centralized control, and less centralized control means more advanced diagnostics. National Grid is currently undergoing this transition on a local scale. They've identified the need for more sensors at substations to check the frequency coming in from IBRs. They've also identified some pitfalls in inverter settings. Inverters are programmed to protect themselves from jumps in frequency and voltage and shut off when the grid goes down. National Grid noticed that inverters will shut off during brief periods of instability. So sometimes this instability only lasts for a few seconds before it's recovered as the grid, gets itself back under it. Now, if a bunch of inverters from a lot of different fields shut down during an event like this, then the grid's going to see a sharp drop in its generation. And this drop could cause further instability as a domino effect of more and more IBRs drop off the grid. So to combat this, National Grid is investigating things like sensors that'll make IBRs more resistant to these types of irregularities. Now, outside of technical issues associated with the inverters, you have the human component. So, due to the massive amounts of funds available for solar power, the industry's exploded. Now you've got a lot of mom and pop solar shops coming up, a lot of startups. And because it's so new, a lot of the trades are hard to come by. Solar fields aren't overly complicated, but, and there are a bunch of electricians that are qualified to do the work, but there's going to be slip-ups, and it's just a numbers game. So if you're installing hundreds or thousands of solar fields, and they're all pushing energy in the grid, there's bound to be some defective inverters, some incorrectly wired systems, and some things working out of spec. So just due to the sheer scale of everything, it'll be harder for the utilities to monitor these systems. Additionally, the individual ownership of the operation of these fields will cause a logistical nightmare for any grid operator trying to get these things back under control. So hopefully the more advanced monitoring and remote control systems will help alleviate these issues as the grid focuses from, more centralized generation to decentralized. Next, Jess is going to explain the technical issues with IBRs.
Thanks, Alex. As a result of the increased number of IBRs on the grid, there have been some issues that definitely need to be addressed. One of these is the intolerance of IBRs to high overcurrent. This pushes the inverters to trip, causing a loss of power more often. Another issue related to these technologies is unstable and unpredictable controls. There's no standard inverter currently that's connected to these resources, which creates high variability in grid impedance, equipment manufacturer, and inverter-to-inverter interactions. Variation in these areas makes it harder for utilities to maintain stable and reliable power because they're unable to fulfill and fully predict how these resources will respond. This leads into a third issue, and that's insufficient modeling. This technology is new and fast growing, so the industry hasn't had time to model the expected behavior under different situations. And so modeling, standardization, and further development of IBR technologies is needed to reduce these issues and interconnect more of these devices into the grid. So there are a few things that can be done by regulatory agencies to lessen these negative impacts that IBRs have had thus far on the grid. The second-to-second and hour-to-hour load changes of IBRs can be regulated by utilities, so their impact on the grid is greatly reduced. And this would ensure that ramping speed required to meet demand during off-peak hours is minimized. Reserves like batteries can also be implemented, so if a power plant trips, power can be provided within minutes to offset the sudden and unexpected loss of energy. So to improve how the grid handles new IBRs, real-time monitoring tools can be used so that they are better understood. Events like faults, generation loss, islanding, and tripping can be detected as soon as possible or prevented altogether. Offline monitoring can also be used to analyze past events and understand how they can be prevented in the future. IBR data like this will ultimately help create trends, which could be used to identify how inefficiencies can be effectively avoided. Overall, IBRs have been a necessary addition to the grid as regulation mandates the adoption of more renewable technologies. However, this comes with a new set of issues, and these need to be understood through the modeling described, which would allow for more seamless adoption of IBR technologies. And ultimately, this would help the US reach its carbon emission reduction goals set to address climate change and global warming. So now I'll pass it off to Ahmed, who will talk about the PJM IBR model initiative.
Thank you, Jessica. Over the past decade, increasing focus by federal and state government on climate change, energy independence, and other policy areas continue to make clear the critical role of the transmission system. PJM is working to outline a vision and present a roadmap for the grid of the future by examining industry trends and the drivers to assess the potential impacts on PJM transmission planning process. The grid of the future is not some far distant idea, but is here now. PJM, like other power grid operators across the United States, has before it a robust, reliable transmission grid, but one upon which enhanced operational flexibility must continue to grow to ensure reliable power delivery 24/7 year-round. With a generation fleet fuel mix shift from conventional generation resources to variable and or duration limited inverter-based resources, a number of key reliability attributes have been identified that will need increased focus to ensure reliable operation throughout the transmission to a decarbonized grid. These reliability attributes include inertia and frequency control, ramping capability, short circuit, and voltage control as discussed with PJM. PJM evolving resource mix and system reliability. PJM recognizes that solar presents its own challenge, such as when low availability of solar power coincides with high power demand. To address this future grid risk, PJM studies must examine time of day and seasonal impact of solar and grid power flow patterns. And as with wind power generation, the inverter-based resources power electronics associated with solar-powered generation also. This also introduces concerns with maintaining or even increasing the availability of such levels of NERC, which is North Electric Reliability Corporation, defined reliability attributes, which is an issue that PJM continues to examine. Thank you.
Thanks, Ahmed. So as we heard, we're transitioning from inertia-based resources to inverter-based resources to meet our climate change goals. With more inverter-based resources comes more problems that the current US power grid wasn't designed to handle. There are some methods to face these challenges, such as monitoring and modeling past problems, so that trends can be identified to prevent future complications from occurring, as we've seen with the PJM initiative. Thank you to Mr. Budhraj for taking the time to present his seminar. Tune in next week for the 5th Zoomcast in the Fall 2023 ESE series.